All right. So thanks for the invitation. So I'll be talking about some work with David Conlon from Oxford and Jacob Fox from MIT. So 10 years ago, Ben Green and Terry Tao proved the remarkable theorem that the prime numbers contain arbitrarily long arithmetic progressions. So I remember first hearing about this theorem when I was still a high school student and being quite excited. Such a simple sounding result, but of course the proof is very, very deep. Okay, so here's some examples of such arithmetic progressions in the prime numbers. And so the purpose of this talk is to explain for you the main outline in the proof of the Green-Tao theorem as we now come to understand it. So we've done some work where we simplify the main technical ingredient in the proof, and I will explain that. So to talk about the Green-Tao theorem, I must also talk about Szemeredi's theorem. So Szemeredi proved in the 70s that if you take a subset of the positive integers with positive density, then the set must also contain arbitrarily long arithmetic progressions. Now, the density is defined in the usual way. So, for example, the even numbers have density 1/2. We know from the prime number theorem that the primes have density decaying as 1 over log n. And so Szemeredi's theorem itself does not directly imply Green-Tao theorem. And in fact, even the best quantitative bounds on Szemeredi's theorem known today are not quite enough to prove the Green-Tao theorem directly. Although for the 3-term case, the best bounds due to Tom Sanders come incredibly close, still yet not enough. It is a famous conjecture of Erdős that the density of the primes alone should imply that they contain long arithmetic progressions. But that's still an open conjecture, and that's something that people would very much love to prove. So then, what is Green-Tao strategy, given that they are not improving on Szemeredi's theorem for the purpose of proving the result of all primes? Well, the strategy is as follows. I first start with my set of primes, P. And they embed these primes in a somewhat larger set. For the purpose of this talk, let's call this set the almost primes. Now, this is not quite an accurate description, but it's a sufficiently good image to keep in mind for our purpose. And you can think of P being embedded in Q as a set of positive relative density. And they show two things. First, they show a relative Szemeredi theorem, which informally says that if you start with a set S, so here S is my Q, and if S satisfies certain pseudorandomness conditions, then it satisfies this relative Szemeredi property, meaning that every subset of S of positive relative density contains long arithmetic progressions. So this is their main technical result in their work. In the second step, they construct such a pseudorandom host. Starting from the primes, they construct this superset of primes, or more generally a majorizing measure, which satisfies the desired pseudorandomness conditions. And for this part, they borrow ideas from, at the time, recent works of Goldstern and Yildirim on small gaps between primes. I will mostly focus on the combinatorial aspect of it in this talk, and this is the part that we improve on. So what do I mean by pseudorandomness conditions? In Green and Tao's work, they require two different kinds of pseudorandomness conditions, which they called linear forms condition and correlation condition. I'll explain what the linear forms condition is in more detail, but the correlation condition, it suffices to say that it's a somewhat more technical condition that seems less natural for the purpose of this particular problem. And it almost feels as if it shouldn't be there. This is a very interesting result, I think, in of its own. And a natural question that arises is, well, what pseudorandomness conditions do you really need to guarantee such a consequence of having dense subsets containing long APs? So can you do with weaker and more natural pseudorandomness conditions on the host set? And our main result is that you can, in fact, completely get rid of this correlation condition, and we can use a much weaker form of Green-Tao's linear forms condition. And I'll explain what our linear forms condition says, and it has, I think, a fairly natural interpretation. So to give an overview of things, so we started out with Szemeredi's theorem, where you can think of it as a result where the host set is all of the positive integers, and relative Szemeredi theorem, where the host set is, instead of the entire set of positive integers, just some sparse set. In both cases, the conclusion is that a relatively dense subset should contain long arithmetic progressions. To put our work in some context, you can ask, well, what about different kinds of host sets? So if you start with a random host set, so for instance, I take 1 to n and I choose each element to be in my set with some probability p, when does it have this property? So this question was first studied by Koyakawa, Gruchak, and Roth in the 90s, where they proved that for 3-term arithmetic progressions, this probability is the correct threshold. So for p above 1 over square root of n, you have this property, and for p much less than that, you don't have that property. And more generally, there was a breakthrough a few years ago by Conlon Gowers and independently Schacht, where they resolved this problem in general for all k-term arithmetic progressions. So this is in the random case. In this talk, I will only talk about a pseudorandom case. And as I mentioned, Green-Tao proved a version of this relative Szemeredi theorem under the conditions of linear forms and correlation. And we prove it under just correlation. In fact, a slightly weaker version of just under linear forms, and a slightly weaker version of their linear forms. Yep.
For the random host set, one direction is pretty easy to prove. Yeah?
That's right, one direction. So for p much less than this, you can show that there's much fewer 3APs than the number of elements in your set. So you can just take out those 3APs and destroy all the 3APs. Right? So it's the existence that's a harder direction. Okay, any other questions? Okay, so I want to first outline a proof of this classic result of Roth on 3AP-free sets. So it says that, so this is a 3-term version of Szemeredi's theorem. It says that if you have a set which is 3AP-free, then it contains a sublinear number of elements. It will be somewhat easier to work in Z mod n because of the cyclic group structure. And roughly these two settings are the same. The only difference is that in Z mod n, you're allowed wraparounds, where the 3APs could wrap around 0. But there's a standard trick to get rid of that, which is to, if you start with 1 to n, then you embed this in a slightly larger cyclic group so that wraparounds no longer cause an issue. So for our purpose, these two settings are really the same, and we'll just work with Z mod n. So let me show you a graph-theoretic proof of Roth's theorem. So this is not Roth's original proof, which is through Fourier analysis, but it's a graph-theoretic proof. And the point of this is to motivate a construction that will be needed to explain the pseudorandomness condition. Starting with my set A, it's a subset of Z mod m, let me construct the following tripartite graph, where I have 3 sets of vertices, x, y, and z, where the vertices are labeled all by elements of Z mod n. I put in my edges as follows. So between x and the set, so between these two vertex sets, I put in an edge between x and y if and only if this linear form 2x plus y is in my set A. Okay, so that's just some rule for putting in the edges. You can think of it as a modified Cayley graph. Similarly, I put in an edge between x and z if x minus z is in my set A, and between y and z if minus y minus 2z is in A. Okay, so these are just the rules for putting in the edges. Okay, so why do I put in these edges? Why do I choose these 3 linear forms? It's because if I think about what are the triangles in this graph, so when do vertices x, y, and z form a triangle? They form a triangle if and only if these 3 linear forms are all in my set A. Okay, so that's just reading off the rules. But these 3 expressions, notice that they form a 3-term arithmetic progression with this common difference. So that's the reason why those 3 linear forms were chosen. So triangles in this graph correspond precisely to 3-term arithmetic progressions in the set A. But I started out with a set A which doesn't have any 3-term arithmetic progressions. So does that mean that there's no triangles in this graph? Well, almost. Not quite, but almost. There are still some triangles because we still have some trivial 3-term arithmetic progressions with common difference 0, and they're still being picked up by this graph construction. So, but these are the only triangles. And in particular, one notices that every edge in this graph is contained in exactly one triangle, namely the one that completes the equation x plus y plus z equals to 0. Right, so to summarize, there's this graph which has 3n vertices, 3n times a edges, so think of it as a Cayley graph, so there are a edges between, so coming out of every vertex between every two vertex sets. And every edge is in exactly one triangle. And there's a nice result of Rusha and Szemeredi in the 70s that says that such a graph, if every edge is containing exactly one triangle, has a subquadratic number of edges. So this is a consequence of what's known as the triangle removal lemma. Using this result, we deduced that the number of edges is little o of n squared, and hence A has size little o of n. Right, so that completes the proof of Roth's theorem. Of course, most of the content of the proof is sort of hidden in this result. And so the standard proof of this uses Szemeredi's regularity lemma. But the point of you showing this proof is not necessarily to show you how to prove Roth's theorem, but I want to use this construction, this graph theoretic construction on the previous slide, and this explanation shows that that construction is related to 3-term arithmetic progressions. Okay. So now I want to explain what is the pseudorandomness condition that we use in relative Szemeredi theorem, in particular relative Roth theorem. So relative Roth theorem for us says the following. If I start with a subset of Z mod M, which satisfies what I will explain, 3 linear forms condition, then a subset of it, which is 3AP free, contains has necessarily to be sparse, relatively speaking, to the host set. And what is this 3 linear forms condition? Well, if I start with this graph GS, so this is the same construction as before, except that I build my edges based on the set S, the host set S. Right, so I draw in these edges using basically the same rules. Then the 3 linear forms condition says that this graph GS is pseudorandom in the following sense. That if I want to count the number of embeddings of K222, so K222 is this object here, then the number of embeddings of K222 should be roughly the same as the number of embeddings of K222 into a random graph of the same density. Right, so if my set S has density P, then the density of embeddings of these things should be P to the power 12th power, up to a 1 plus little o1 multiplicative correction. We need just a bit more. We want to say that not just for K222, but also all subgraphs of K222. For example, this thing should also have the correct number of embeddings. But that's it. Right? So just saying that these subgraphs have the correct number of embeddings, that's all the pseudorandomness conditions that we need, and this guarantees this relative Roth theorem. So that's the result. Yeah.
Say a word about why K222.
Okay, so so this is my next slide. So let me draw some, okay, so of course K222 comes out of the proof, but just to convince you that it's a natural condition, let me draw some analogies to some classical results about quasi-random graphs. So in the late 80s, Chang, Graham, and Wilson have this famous result that, so they explored the notion of quasi-randomness in graphs and show that there's a number of different definitions, all of which are equivalent. And one that in particular that stands out, so some of these conditions are eigenvalues, co-degree conditions, subgraph counts, and so on. But there's one condition that stands out as having the correct C4 count. And just having the correct C4 count is equivalent to a host of other pseudo quasi-randomness conditions. But just for dense graphs. So their results only work for dense graphs. And they break down if you have sparse graphs. One way to see our result as an analogy to this type of result is that if I want to study some extreme or Ramsey type result about a graph H, so for the purpose of Roth's theorem, H is a triangle, as we saw earlier in the graph theoretic proof of Roth's theorem. So if I want to know some extremal results about the triangle in a sparse graph, then I have everything I need, provided that there is some host graph which behaves pseudo-randomly with respect to the two blow-up of the triangle. So that's one way to remember this result. And in retrospect, you can view Chung, Graham, and Wilson as saying that I have knowledge about dense graphs if I know the correct count of the two blow-up of a single edge. Whereas for sparse graphs, if I want to know something about triangles, I need to know the two blow-up of a triangle. Okay, so that's just an analogy. Okay. So more generally, relative Szemeredi theorem, we have longer arithmetic progressions, or KAPs, says the same thing, except I switch out this 3 linear forms condition by what we call the k-linear forms condition. And that's a natural generalization of this graph theoretic construction, where now instead of taking graphs, I now take a hypergraph. So for example, for 4-term arithmetic progressions, I built for you a 4-partite, sorry, there's no weighted here, so 4-partite, a 3-uniform hypergraph. So all the vertex sets are Z mod n. I put in my edges according to these rules, very similar to the rules that we saw earlier. And so these rules are chosen so that these linear forms, they form a 4-term arithmetic progression, so just like what we saw earlier. And the pseudorandomness condition is that this graph constructed here, this hypergraph constructed here, has the correct count of the two blow-up of the simplex. So the simplex is the complete 3-uniform graph on 4 vertices. So they're the faces of a tetrahedron. And that's it. So it's just it's a natural generalization of what we saw in the 3 case. For the rest of the talk, though, I will just talk about the 3 AP case. It turns out, so if you're familiar with Szemeredi's theorem, you know that in all different proofs of Szemeredi's theorem, actually all of the proofs are difficult, but in all the different proofs, the 3-term case is substantially easier than the longer version. It turns out, though, for the purpose of proving relative Szemeredi theorem, and I'll outline the strategy of the proof on the next slide, for the purpose of proving relative Szemeredi theorem, there is no, at least the way we do it, there's no technical difference in difficulty between 3 AP or longer AP. The notation gets a bit more clumsier, which is why I don't want to talk about longer APs. But the substance of the proof is all contained in what I will explain for 3-term arithmetic progressions. So I'll just do 3-term from now on. Okay. So there's a couple of different approaches. We first arrived at this result in this paper that titled A Relative Szemeredi Theorem, where we transfer the hypergraph removal lemma. Okay. So this is one of the ways of proving Szemeredi's theorem through this hypergraph removal lemma. And we transfer it, meaning that we assume this hypergraph removal lemma is a black box and transfer it down to a sparse setting. Subsequently, I found a different approach of proving more or less the same result, where instead of transferring a particular way of proving Szemeredi's theorem, I transfer Szemeredi's theorem directly, meaning that if you start with any proof of Szemeredi's theorem, for example, any Fourier theoretic proof or anything, then I can transfer that proof and its bounds down to the sparse setting. And so this is the approach that I will explain in this talk. It's somewhat more direct, whereas this hypergraph proof is somewhat more general, and it could be applied to some other situations. And this is a short note. Okay. So So here's an outline of what the proof of relative Roth theorem is. So I start with relative Roth theorem. One way to say this is that if I fix a delta, then any such set with a least density delta should contain a 3-term arithmetic progression, provided always n is large enough. It will be helpful, and there's a standard averaging argument, to go from this version of Roth theorem to a counting version where I get not just one 3AP, but many 3APs, a quadratic number of 3APs. Okay, so this is a fairly standard argument. Roughly it goes like this. If I start with a set A that has this density, then I just sample a AP of length n naught, where n naught is some large but fixed constant. And then by this version, I see at least one 3AP. But if I keep sampling, then I would see a quadratic number of 3APs. So it's a standard sampling argument. From this counting version, then we can prove this relative Roth theorem using the following outline. So I start with a sparse set of, so a sparse set A contained inside some pseudorandom S. The first step, we find a dense model, A tilde for A, where A tilde is an approximation for A in some cut norm sense that I will explain later. But the main thing to remember here is that A tilde is a dense subset, and the density of A tilde in Z mod n is roughly the same as the relative density of A in the set S. And then there will be another step called a counting lemma, which will tell us that if A tilde is a good approximation for A, then the number of 3-term arithmetic progressions in A will be similar to that in A tilde once you do the appropriate normalization. But we know from the counting version of Roth's theorem that because A tilde is a dense set, that A tilde should contain many 3APs. Okay? And this would then imply that A also contains many 3APs. And that basically concludes the proof of the relative Roth theorem. Right? So at this point, you already know that A contains many 3APs, and we're pretty much done. Of course, there's these two steps, and I need to explain what are these two steps. So this was the counting version of Roth's theorem that we saw earlier, that A contains many 3-term arithmetic progressions. It will be convenient to work with instead of a discrete version, a weighted version of Roth's theorem, where instead of taking sets, I now put weights on my elements of Z mod n. And these two results are equivalent up to a change of constants. So this version says that if I start with any function on Z mod n, taking bounded values, then the 3AP density in my function f, right, so this expression here, so where if f is an indicator function of a set, then this is precisely the 3AP density. And the 3AP density in the function f is at least c, provided n is large enough. So this is just the weighted relaxation of the usual counting version of Roth's theorem. It will be convenient to use this for a couple of reasons. One is that in the proof, having weights really helps. The second reason is that if you actually want to prove the Green-Tao theorem about primes, it would be much better to use a weighted setting, where instead of taking majorizing sets, you take majorizing measures. So from now on, we'll switch over to the weighted setting, so the functional form of everything. But this is a weighted version of Roth's theorem for dense sets. Right, so for the dense version. So what would the sparse version correspond to? If I start with some sparse host set, S, then this corresponds to a normalized measure nu, where you can think of nu corresponding to a set S as the normalized indicator function, where I just normalize it so that it has expectation 1. Okay. So in particular, nu will not be bounded by 1. So there's a scaling that happens here. Then the subset A of S, relatively dense subset, will then correspond to a function f which is majorized by nu. So this is the condition that corresponds to being a subset. And f will also have expectation at least delta. So this is the condition that corresponds to being relatively dense. Then a relative Roth theorem says the following. Yeah, sure. Yeah. Any questions? Okay. So here's a statement of our relative Roth theorem. If I have a majorizing measure nu, which satisfies the 3 linear forms condition. So this is basically the K222 condition that I mentioned earlier, but I will say it again on the next slide. And any function f which is majorized by nu, and the expectation of f is at least delta, then the 3AP density in f is bounded from below. So this is the sparse extension of the dense version of Roth's theorem. And this 3 linear forms condition says the following. Essentially, it's about the density of the K222 object in.
Sorry, could you go
Yeah.
back one second?
Yeah.
Don't you need to, in the last equality, to normalize by the density of?
So everything is already normalized.
Oh.
So you should think of this as having constant expectation order.
Oh, okay.
Right? So that's why there's no normalization, because it's already part of the normalization. Yeah, so f is not just the indicator function, but normalized in the same way that nu is. Yeah. So the 3 linear forms condition basically says that the density of K222 in this weighted graph, right? So it's the weighted analog of what we saw earlier, that this density is correct, so 1 plus the total 1. And if I just write out the whole thing, it would say that this expression here is 1 plus the total 1. As well as if any subset of these 12 factors were deleted. And this is the complete statement of our result for relative Roth theorem. Okay. Now, how do we prove this result? Well, so this is essentially the same transference slide that we saw earlier, but now written for the weighted form. So I want to prove this about nu, f and nu. So these are sparse objects. The dense model theorem, the first step, says that we can approximate this f in terms of this cut norm by a dense object, f tilde. So dense basically means that it's bounded. Sparse means that it's not bounded. We want to normalize so that everything has constant expectation order. The second step is a counting lemma, which says that if I have this approximation, then the 3AP density in f should be roughly the same as the 3AP density in f tilde. And we know from the weighted version of Roth's theorem that the 3AP density in f tilde is bounded from below. So this then implies the relative Roth theorem that the 3AP density in f is at least c, basically. Yeah. Okay, so let me explain now these two steps. First, the dense model theorem. So in what sense does this dense model f tilde approximate the sparse object f? So in the previous approach taken by Green-Tao, they used some notion which is based on the Gauss uniformity norm. Our main simplification here is that we do not at all use the Gauss uniformity norm. Right? So we use something much weaker, which is the cut norm. It's also known as discrepancy. And the advantages, okay, so how do these two approaches compare? The advantage of using the cut norm is that we obtain a much cheaper dense model theorem. Cheaper meaning that we require fewer pseudorandomness hypotheses. The expense is that it requires a trickier counting lemma, and this is really the main technical advance in our work, that we come up with a new counting lemma based on the cut norm instead of the Gauss uniformity norm. Okay. So what is this dense model theorem? So let me first remind you what the cut norm is. So if I start with a weighted bipartite graph between sets x and y and some weighted graph g, so I can define the cut norm of g to be this quantity. And essentially it says that the cut norm is small if whenever I take a large set A and large set B here, then the sum of the edge weights between A and B is never too large. So somehow the edge weights, they all cancel out. So, but precisely, it's this expression here, that's the cut norm. From the cut norm definition for graphs, I can define a cut norm on functions on Z mod n. So starting from a function on Z mod n, basically I construct a bipartite graph where the edge weights are given by f evaluated at x plus y. And then I take the cut norm of that graph. So written down, it looks like that. So it's the cut norm of this associated graph. So this is the norm on Z mod n. And the dense model theorem then says the following. If I start with a nu which satisfies the following actually rather weak pseudorandomness condition, which is that nu is close to 1 in this cut norm, then every function majorized by nu can be approximated by a dense model f tilde. And this approximation also is in terms of this cut norm. Okay, so that's the dense model theorem that we will use. Okay. Say again? So, yeah. Right. So it happens because of the normalization. Right? So you should think of the expectation of f and the expectation of f tilde as the relative density in the host sets. So f as a set is sparse, but because I start out with nu, there's a normalization that boosts up the weights. Right? So when I take the expectation of f, that's the relative density of f in the host set. And them being close in cut norm, in particular, implies that they're close in the expectation. So if you just take A and B to be the whole thing, then it means that they're in particular close in the expectation. Okay, so how does one prove the dense model theorem? So I won't actually show you the proof, but let me just outline some of the different approaches. So there's a more general dense model theorem that applies to other norms, and in particular, the original intention of Green-Tao is to apply it to this variant of the Gaussian uniformity norm for the purpose of proving their result. And the original approach was to prove this general dense model theorem using a energy increment type argument, similar to what you would do to prove the regularity lemma, Szemeredi's regularity lemma. There was a subsequent simplification due to Gowers and independently Rengel, Trevisan, Tusiani, and Vadam, where they came up with a very neat proof that's much shorter that involves two ingredients. The first ingredient being a separating hyperplane theorem, also sometimes known as the Hahn-Banach theorem. These guys phrased it as the minimax theorem. Roughly, they amount to the same thing. And the second step involves a Weierstrass polynomial approximation theorem. So these are two different approaches, and this one is considered a simpler approach that was found subsequently. So it's quite simple, and that's in fact made even simpler. So there's an additional observation that says that if you look at this proof and specialize it to the cut norm, then essentially amounts to saying that the dual objects to the cut norm is closed under multiplication. So that's not true for the Gaussian uniformity norm, but it is true for the cut norm, that the dual objects are closed under multiplication, and that really simplifies things a lot, and that's part of why we get much simpler pseudorandomness conditions. So with those observations, so we have this form of the dense model theorem that we'll use for relative Szemeredi. So this is weaker than this three linear forms condition. So it's in particular implied by the three linear forms condition. I don't really know how to explain more than just saying that it's the cut norm being small. But it is weaker, much weaker than even actually this having small Gaussian uniformity norm. It's quite weak. Okay, So what about for longer arithmetic progressions? So I said I won't really go into what longer arithmetic progressions are, but let me just say a little bit about what the correct generalization is. Let's say for 4-term arithmetic progression, so we saw that this involves a 3-uniform weighted hypergraph between, and the correct generalization of the cut norm that we use here. Okay, so the first thing you might come up with is you take subsets of vertices and evaluate the sum of the edge weights. Okay, that's not quite the right thing to do. The right thing to do is instead of taking subsets of vertices, and now I take a subset of pairs. So I take an underlying 2 graph and evaluate the discrepancy on top of that 2 graph. And this is it's a fairly standard thing to do if you ever talk about hypergraph regularity, for instance. But so that's the generalization for hypergraphs and for longer arithmetic progressions. But other than this, everything else is more or less the same. Okay, so that was the dense model theorem. The second step I want to explain, essentially the main technical advance in our work, which is the new counting lemma, the sparse counting lemma. It says that if f and f tilde are closed in this cut norm, then they share similar 3AP counts. Okay, so first let me explain the classical counting lemma for the dense setting. It will be much easier to do this for graphs, and you'll see it's a lot more intuitive. So let's forget about the arithmetic setting for now and just think about graphs. Let's say I have 2 weighted graphs on, so 2 tripartite weighted graphs, G and G tilde. First, let's think about the dense setting. So dense setting, again, means that they're bounded. The edge weights are bounded. The triangle counting lemma says that if G and G tilde are close in this cut norm, then the triangle densities, so this is the expression for the triangle density, the triangle densities of G and G tilde are close, as long as they're close in cut norm. Okay, so let me show you how to prove this. The proof is very short. Recall the definition of the cut norm. One way to phrase it is that if you have G and G tilde, then if I restrict this expectation to any subsets of vertices A and B, then this expectation is never more than epsilon. So this is just a rephrasing of the definition of the cut norm. More generally, I can replace subsets of x and y by functions, bounded functions on x and y. Just because if you look at this expression here, it's bilinear in these 2 factors. So it's bilinear in these 2 factors. So if I want to obtain the extrema for this expectation, allowing myself to vary A and B, the best way to do it is to take A and B at their extreme values, namely 0 and 1, and then that just becomes a set version. So these 2 versions of the cut norm are equivalent. But now let's take a look at the triangle count. So let me start with the triangle counting G. I claim that I can swap out one of the blue factors. So blue is G and red is G tilde. So I can swap out one of the G by a G tilde at a cost of at most epsilon. The reason is that if I look at the difference between these 2 expressions here, it precisely has this form if I fix a particular value of z. Right? If I fix any value of z, then the difference has this form, so it's bounded by epsilon. So now I let z vary, then the expectation is still bounded by epsilon. So this allows me to swap out one of the factors, and I can do exactly the same thing to the 2 other factors. Okay? And at the end, I obtain that T of G differs from T of G tilde by at most 3 epsilon. And this completes the proof of the triangle counting lemma in the dense case. Now, what about the sparse case? So sparse, as we recall, corresponds to when, let's say, G here is unbounded. This entire proof breaks down from step 1, because if I look at the difference of these 2 things, then I can't use this condition anymore, because G is no longer bounded. So one has to do something else. Right? So and this becomes potentially quite tricky. So here's our main technical advance, which is the a new sparse triangle counting lemma. It says that if nu satisfies this 3 linear forms condition, meaning, well, so this is what we saw before, this K222 condition, then we have a counting lemma provided that one subgraph is majorized by nu, then the other subgraph is dense. Then there's a triangle counting lemma. Okay, so how does the proof work? I won't tell you the whole proof, but just I'll highlight some of the elements. So there are 3 main ingredients. The first is repeated applications of the Cauchy-Schwarz inequality. So this is a standard technique in this area, as popularized by Gowers through his uniformity norms and his works there. So I won't go too much into this, but it's one of those things where if you've seen it done once, then you'll sort of recognize it here. There's a lot of Cauchy-Schwarz applications. Okay, so the main thing which we introduce is this technique that we call densification. I will explain this on the next slide. We also reduce this problem to the dense case that we saw earlier. So somehow we reduce the sparse version to the dense version. So let me explain what this densification step is. So Cauchy-Schwarz, okay, so many applications of Cauchy-Schwarz roughly corresponds to each step doubling a vertex. So there's a square involved. Whenever you have a square, a vertex gets doubled. So if you want to count triangles, one of the intermediate steps that you get happens to be this 4th cycle. Right? So somehow this is a natural obstacle. If you want to count triangles, you better know how to count this guy. Okay, so this comes up, for example, if you start with a triangle and then look at one vertex and double that vertex as a result of the Cauchy-Schwarz. So let me explain how do I prove a counting lemma for counting this 4th cycle. So the 4th cycle is this expression here. Well, let's see. Let me create an auxiliary graph called G prime. G prime is defined by this formula, but basically what it is that it records the codegrees, the common number of common neighbors. It records the codegrees between vertices in x and y. This is, by the way, where having weights really comes in handy. Like everything else I said before, more or less you can do the same thing without weights, but this step, introducing weights, really helps a lot. Even though we started out with a graph or weighted graph, which is sparsely supported and unbounded, once I take codegrees, things become a lot nicer. They become a lot smoother. So the codegrees are more or less bounded. And this is partly because of the pseudorandomness conditions that we assume on the host set. But the point is that the codegrees are more or less bounded. You can think of them as, okay, so they're basically bounded almost all the time. And so let's just think about the G prime as a bounded graph. This allows me to replace 2 of these factors by a G prime. And now I've arrived at this expression here, which is a triangle count expression. So we went from initially counting triangles, and I said that through some Cauchy-Schwarz, one of the things to reduce the counting is a 4th cycle. And through this reduction, we've somehow gone back to counting a triangle. So at first, it seems like we've gone back in a loop. But we gained something really important, which is that we swapped out one of the pairs, which was initially sparse, by something which behaves like a dense graph. Now, just do it 3 more times. Oh, 2 more times. Right, so do it 2 more times. And then we've reduced the whole problem to the dense version of the triangle counting lemma, which we know how to do. Okay, so then this is the rough outline. And this is the main new idea in the proof of the triangle counting lemma. Okay, so this is an outline of the proof of Roth's theorem. So I explained to you what the dense model theorem is about, and also showed you some aspects of the counting lemma. And then combining everything, you get a proof. And the whole thing is not very long. So of course, I don't have time to go into all the details of this proof. But if you want to learn about the details, so we're finishing up an exposition of the Green-Tao theorem, where we give a gentle exposition containing a complete and a self-contained proof of the Green-Tao theorem, also including some of the number theoretic estimates, which are also not too hard. with one caveat is that we have to assume Szemeredi's theorem. So that's a heavy gun that you're not going to be able to prove in this short exposition. And it will be around 25 pages. So we're finishing this up as we speak, and hopefully it should come out really, really soon. And so if you want to learn more about this proof, so that hopefully we'll put on the archive within the next couple weeks or so. And with that, I want to thank you for your attention.